This lecture is going to cover metamorphic rocks and some basic processes. Be sure to watch this video. I should have screencasted and loaded this to a community page already, but I go through some of the rock samples, the metamorphic rocks, both foliated and non-foliated, that we'll be looking at. So here we go. It all starts with us looking at rocks in the Earth's crust. We'll look at the percentages by volume. That the igneous rock section, or the type of rocks, are really dominant. About 2/3 of all rocks within the Earth's crust are igneous, and about 2/3 of those are basalt. Just by kind of mentally envisioning the Earth itself, you'd see that the Earth is dominated by ocean water. Oceans are covering, let's just say, oceanic crust, and oceanic crust is basalt. So hopefully just a mental picture of the Earth gives you an idea of the significance of basalt. The next group is metamorphic. Metamorphic rocks cover about 27% of the Earth's crust, or compose it. And gneiss dominates that by about 78% of it. And lastly, a small grouping are sedimentary rocks, and shale is the dominant sedimentary rock. And here we can look at that same breakdown, and this just kind of breaks out the rocks in the Earth's crust of metamorphic. Here we can see that gneiss is 78%, schist is about 19%, and then marble and other metamorphic rocks are kind of the remaining 3%. And for sedimentary, we're talking shale and kind of siltstone, right? You're generally speaking your mudstones at 70%, sandstone about 15%, limestone at about 10%, and then just kind of other sedimentary rocks 5%. And then igneous, we're talking about basalt and others are about 66%, right? We're talking about dark colored mafic rocks that are dominated by mafic minerals. And then granite and other kind of felsic mineral containing rocks kind of make up that missing, or the extra 34%. Moving on. So when we look at metamorphic rocks, let's go back to the rock cycle. We've already studied igneous rocks and processes. We talked about the process of melting and crystallizing. When we look at sediment, we're talking about either the breakdown or the precipitation. So in this case, where you have sediment, you have detrital. Sometimes they precipitate out and form your chemical and your biochemical sedimentary rocks. But now we're looking at metamorphic rocks. That an igneous rock, a sedimentary rock, and even a pre-existing metamorphic rock can be metamorphosed into another type of metamorphic rock. Metamorphic rocks are formed at variable depths within the crust when pre-existing rocks, including igneous, sedimentary, and even older metamorphic rocks, are changed physically and chemically due to the change in temperature, pressure, or both. During metamorphism, the texture or mineral composition, sometimes even both, of pre-existing rocks change under various metamorphic conditions at different depths. Here we can look at figure 5-25, and we can actually see this. So here's a kind of a cross-section, a cutout of just kind of a general cross-section profile. And we see slate is kind of a low temperature, low pressure. It's kind of a shallow rock that forms under kind of minimal temperature and pressure. If I keep on metamorphosing slate, I can get phyllite. Phyllite's a little deeper, a little bit more temperature, a little bit more pressure. Phyllite can eventually become schist, deeper in the earth, right? Greater temperature, greater pressure. And lastly, we get gneiss. Gneiss would be kind of a high temperature, high pressure type of rock that has these very nice, obvious foliations. In this case, we call these bands of minerals. Temperature, pressure, and chemically active fluids change pre-existing rock into something new. When we talk about high and low-grade metamorphism, we're going to talk about gneiss being a highly foliated type of rock, right? It's a high grade of metamorphism. And then slightly less than that is schist. Schist would be still a higher grade, be kind of a medium grade. Phyllite would be a lower grade, and slate would be kind of a low-grade metamorphic rock. But these are the four primary foliated types of rocks that we're going to look at. I like this picture because it illustrates a subduction here. And it's really a convergent boundary. And plate boundaries are where all kinds of geologic activities are taking place. Here we find a subducting plate at a convergent boundary. We can find volcanism, we find partial melting. We also find metamorphism of rocks. We have the temperatures and pressures, let's just say, in this scenario, that lead to the formation of mountains and kind of the changing of pre-existing rocks. That this region illustrates a wide range of temperatures and pressures. So you get a wide range of types of rocks that form. So here we can look at the greater the heat, or the greater the temperature, and the amount of time, the greater the degree of metamorphosis. So we might have this low-grade, kind of mildly metamorphosed rock. If I continue adding heat and pressure, it can be formed into slate. Adding more increasing metamorphic grade, we're talking, we can move into schist. What's missing from in here is phyllite. Phylite's a nice little intermediate between slate and schist. If I continue increasing temperature and pressure, I get this nice, this rock actually called gneiss, and it has these bands within it. Pre-existing rocks change due to metamorphosis, thus the name. And this is a picture you're going to need to get used to. You're going to need to make sure you pay attention to textures. We can talk foliated and non-foliated. And you will need to know all of these different types of rocks. But I want to pay attention here for a moment at grain size. That the texture matters here. That the grain sizes of slate are very, very fine. And phyllite are also fine, but not quite as fine as the slate. As I move on into schist, these can be medium to coarse grained, right? And these are kind of pictures. I mean, I can't really tell you much with these pictures here. There's not a whole lot going on. But we can say medium to coarse grain or texture. And then when we look at gneiss, it has these very obvious banding. These are very important. We'll talk about these as we move on. We'll talk about what differential stress is. But these are my foliated rocks. These are my foliated textures. When I look at what's going on here, I'm talking about increasing metamorphism. Gneiss is the highest degree of metamorphism in terms of the foliated rock groups, and slate is the lowest grade. Each of these foliated rocks has a parent rock that came from something. If it metamorphosed, it means it came from something into something. So shale can become slate, or any mudstone for that matter. Slate then can become phyllite. Phyllite can then become schist. And schist and even granite can become gneiss. Just add the temperatures and pressures to change them while they're in the solid state. I want to look at the three non-foliated for a second. These are generally the marble and quartzite. These are medium to coarse grained. Notice that they have intergrown crystals. The difference is that marble will effervesce in the presence of HCl. If it's limestone, it'll effervesce vigorously. If it's dolostone, it'll effervesce mildly. That these would be the parent rock to marble. And thereas quartz sandstone is going to be the parent rock to quartzite. And under the right conditions, you're squeezing these, you're compressing and adding some heat, and you're changing the individual grains of sand into interlocking grains. So that's very key. And the last one is anthracite coal, that its parent rock is bituminous coal. If I add heat and pressure, I get it to this high-grade anthracite coal. We'll talk more about that in a minute. Metamorphic rocks have parent rocks. A metamorphic rock was changed from a parent, the original rock, to another different rock. In the graphic, we see how a parent rock is altered in its solid state to become metamorphic rock. I'm going to emphasize, slate comes from different shale and mud rocks. If I continue adding temperature and pressure, you'll find that shale can become any one of these types of rocks. It can become slate, adding heat and pressure can become phyllite, can become schist, can become gneiss. However, marble's parent rock, depending on its effervescence, is going to determine what type of carbonate it came from. Quartzite, quartz sandstone, and anthracite bituminous coal. I want to look at what direct pressure does. It actually leads to stress. Under directed pressure, called stress, newly formed sheeted and elongated minerals such as mica and hornblende tend to grow along the direction perpendicular to the compressional forces, or the stress. So let's look at this. Before metamorphism, you have all these different minerals kind of contained within here, and we can look at this rock here. This is probably a granite, might even be some form of a diorite. By undergoing stress, right, stress from opposite sides, or differential stress, I can actually align these minerals, and they align themselves in a certain way. The resulting parallel linear alignment of sheeted or elongated metamorphic minerals is defined by foliation. So if I squeeze on either side of this, much like the picture up here, and I have more pressure from the left and the right, these minerals are going to have a tendency. Which minerals? Well, mica and hornblende in particular are going to elongate into these very nice bands that we're going to call, and this is just imply foliation. These are forms, these banding are just high amounts of differential stress. That stress changes everything. So I have these randomly arranged minerals, and then once I have stress from the sides, they're going to align themselves. During deformation, where stresses are not uniformly oriented, many metamorphic rocks develop textures in which the mineral grains have strongly preferred orientations in the direction of the least stress. The resulting mineral alignment often gives the rock a layered or a banded texture called a foliation. It's Latin for splitting into leaf-like layers. So differential stress is going to align these minerals into this area that we call foliation. But the degree of metamorphism varies, and these are what we call index minerals. And these index minerals form under certain temperatures and also certain pressures, but we're only going to look at this from a temperature standpoint. And you can draw lines in here to kind of have this here's a temperature range at 300 degrees Celsius, that you're going to find the likelihood of finding chlorite, epidote, and muscovite. These are lower temperature, lower degree minerals in this case. Here's 400 degrees, 500 degrees. Notice you get a wide range at 500 degrees C. 600 degrees, you get a smaller range, 700 degrees C and even 800 degrees C, different temperatures. So you can see approximate temperature ranges over which some representative index minerals, metamorphic minerals, are stable. Low temperature, low grade. So chlorite, epidote, and muscovite often appear in low grade metamorphic rocks. Intermediate temperatures, which would be intermediate grade. Biotite, hornblende, staurolite, and some garnet. In high temperature, or high grade, right, the higher temperature range over here. Pyroxene, garnet, I'm looking at pyroxene, garnet, and biotite mica, here's my biotite. These minerals appear in high-grade metamorphic rocks. So that the minerals indicate different temperatures and the conditions in which formed them. So when we look at foliated metamorphic rocks, we would say that gneiss has is very highly foliated. Whereas your garnet schist and your mica schist is going to be, let's just say, a high grade, but not as highly foliated as your gneiss. And we have our phyllite, and we have our slate here. That slate is what's considered kind of a slate fracture cleavage, whereas phyllite has a slaty cleavage. Schistosity is a measure for schists. And then we have gneissic banding, which we'll just end here with gneiss. And this is just from low grade, right? These are generally fine grained here. And as we increase in the grade, we increase in the size or the texture of the coarseness of the individual mineral grains themselves. So we've come to the conclusion that rocks become other rocks, and the term is protolith. That means pre-existing or parent rock can be sedimentary, igneous, or metamorphic. But we can see how shale, the parent rock or the protolith, can become a wide range of metamorphic rocks based on the temperature, pressure, and time in which it was changed. So here I have shale. If I add temperature and pressure, it could become slate. That slate can become schist, and by adding temperature and pressures, we can align these minerals, your hornblendes and your micas. And the lighter ones happen to be generally quartz. In this case, we can have these very obvious banding that we call gneiss. But non-foliated metamorphic rocks look a little bit different. Marble is going to effervesce in a weak acid due to calcite, and if it's dolomite, it would effervesce mildly. Quartzite are interlocking grains of sand grains. And left, we would have we see anthracite coal. It's the highest grade of coal. It's generally called clean coal. It's been metamorphosed from bituminous coal. When we look at non-foliated metamorphic rocks, and we look at them under a magnification lens, we get to see so much more of the story, right? Viewing these metamorphic samples under a microscope tells a much deeper mineralogic storyline. Here we see exactly how the parent sample compares to the metamorphic sample. So here's sandstone, individual sand grains. Here we see quartzite. They're intergrown samples. The protolith of limestone is going to have shell fragments. The marble is going to be the metamorphosed. These are going to be interlocking calcite minerals. So you see that they become different because they are different. They've been metamorphosed, which means changed. Here we can look at sandstone, becomes quartzite. Quartz sandstone is squeezed into quartzite. Individual sand grains cemented together are fused together under increased temperature and pressure. So quartzite we have interlocking. Sandstone we have kind of individual sand grains. Here's a cool topic that applies here. It's called impact metamorphism in shocked quartz. When there's a high amount of energy that's in a collision, such as an asteroid impact, we get changes to the quartz itself. It's called shocked quartz. That this here is Barrington Crater. It's Meteor Crater. It's in Flagstaff, Arizona. The shocked quartz is the result of high energy impacts, also found at nuclear test facilities. But they are only found where we have tremendous amounts of energy. And in this case, volcanism doesn't even provide the energy necessary. If we were to look at a quartz grain, and this is magnified about 100 times, we actually see these particular intersecting shock lamella. So we see these characteristic signatures, and this is actually telling me this is shocked quartz. Where you find shocked quartz, it's safe to say that there was likely an asteroid impact or a nuclear event. But more often than not, asteroid impacts have taken place along Earth's history are not uncommon. There just happen to be a signature or a key feature. And last but not least, we'll look at shatter cones. The Kentland Quarry is a site of local shatter cones where limestone bedrock is metamorphosed into a distinctive shape of an impact. The horsetail-like feature or shape is the result of energy transmitting as the shock wave moves through the bedrock. So 97 million years ago, there was an impact that was so powerful that the sedimentary rock strata actually are vertical. They are not horizontal the way we find them